Can you see my screen?
Yes.
Perfect.
Yes.
Okay.
So maybe I just do a little bit of introduction, then
Yeah.
I have someone maybe read your citation, and we can start. Okay,
Yeah, sure.
nice. So you are all welcome to the numerical analysis seminar series that we hold every third Wednesdays of every month. And today we'll be having a very wonderful speaker, Dr. Victor Michel-Dansac. And I will say that I and Victor met by providence, and ever since there has been a lot of collaboration together to and to help ourselves. Let me just use that language and advance mathematics and to find how we can help to develop mathematics in Africa, because that's just my goal in contributing my own little way to help the community over here. And he buys with the vision, and ever since he has been of help to me, in trying to prepare proposals that will help us advance numerical analysis in Africa and Nigeria at large. And, we have been meeting now for, this is about, let's say, this will be the 16th month that we started this seminar series. And we just thank the Almighty God that ever since we've been getting very beautiful speakers to talk to the community, and my goal is just to help graduate students and young researchers to be able to redirect their research, because numerical analysis in Nigeria, the research direction is actually just in one direction, and I'm trying to see how people can benefit and ask very thoughtful questions, and how to shift their mind into very great application and problem solving, because there are a lot of problems that we can solve in Africa here with numerical analysis.
I
So
agree.
you're all welcome to today's seminar series. And before we start, I'll ask Ms. Festa to read the bio sketch of the presenter. Ms. Festa, over to you. Ms. Festa, are you there? Ms. Festa, you are muted. Ms. Festa, are you there?
I've
Can you hear
unmuted.
me?
Can you hear me?
Yes, okay,
I
okay, I
just
can hear you.
forgot.
Yes. Please, can
Can you
you
hear
read
me
the
now?
citation? Yes, we can hear you.
Okay. So Dr. Victor Michel-Dansac worked as a permanent researcher in the project team Macaron of the INRIA Strasbourg Research Center, located at IRMA from LMJL, Nantes, in September 2016. Following his PhD, he embarked on a postdoctoral journey. Okay, I missed something. So in Strasbourg, France, since 2020, he earned his PhD from LMJL in September 2016. Following his PhD, he embarked on a postdoctoral journey from first at IMD from August 2017, and then from September 2017 to August 2020. Dr. Michael's contribution to the field have been recognized through grants, such as the ANRJCJC project called SMEGO. His research areas encompass several topics, including scientific computing and the development of numerical schemes. Since he arrived in Strasbourg, he has started to work in the area of scientific machine learning, enhancing numerical schemes with techniques from machine learning. Thank you.
All right. So now that you have introduced Dr. Victor Michel Dansac, then Dr. Victor, yeah, over to you.
Yeah, okay, thank you. So thanks a lot, Julius. And yes, I'm very glad to be here because, as you said, it has been a very long time since we started communicating only by email, and we have done quite a few grants together. And when I say we have done quite a few grants, it's more like you have done the grants, and then you have asked me for advice, and I said, but I don't have anything to say. It's perfect. So okay, so and you yes. So I will be very happy to host you in September for your visit. Okay, so once again, thank you for the invitation, because I think it's a very nice idea to have this colloquium every month. And so today I will present some of my work that I have been doing in Strasbourg since I joined in about 5-6 years ago. And so, as Festa said, I indeed started to work on hybrid methods, so trying to hybridize classical methods and machine learning, and trying to see what everything like that works. So the goal of this work is not necessarily to give you very precise research directions, but more like to give you an like a general overview of the topic of hybrid methods, and more specifically to give you an in-depth introduction, let's say, to what is the main difference between methods, numerical methods that you are used to, so linear, that I will call linear methods, so finite differences, finite volumes, etc., and the main difference between those and methods based on, let's say, machine learning. And at the end, I have a little contribution from our work that we did with all of these people, and it's mostly during the context, in the context of the PhD of Frédéric Lecourtier. Okay, so let us start. I will start with a bit of function approximation, so there will not be any PDEs until slide 16. So in numerical analysis, what we usually try to do, what we usually want to do, is to, given a differential operator, so given some differential operator D, which can be, I don't know, a Laplace equation, which can be a
Victor. Sorry
Yes.
to cut you there, sorry. The screen seems as if some text
it's frozen.
yes, as if some text are inside, as in outside the frame.
Okay. So wait. Okay.
Maybe you could do a full view or something. Maybe you could do a full screen view.
Yeah. I'm trying. I did that actually, but full screen. Is it better that way? I need to wait. I need to. No, I don't know. I don't think it will be better that way. Wait, give me 1 sec. Presentation. Do you see everything here, or is it some?
No, see outside the frame. Outside the
Okay,
frame.
that is strange. Okay, I will stop sharing and then go back to share again, because maybe that is okay. Here, oh, okay. I seem to. Is it okay? Because on the preview, I seem to have everything. Is it okay right now?
Outside it's still outside the frame.
Still outside. That is strange, because on the preview that I see,
and
everything.
maybe because your camera is showing at the right hand side. Could that be a reason? Maybe it's taking some space.
I don't know. Because
but it's fine here.
It's okay for me.
So for you it's okay, but not for
Yeah.
Julius. Okay. Interesting.
Okay. If it's fine for everybody, then maybe we can. Okay, fine. Maybe then you can continue. Yeah.
But it's sad.
Julius, you might disconnect and reconnect again.
Okay, maybe.
Yeah, I try to disconnect and reconnect. I come back. Okay, sorry, I was muted. So is there still an issue, Julius, with my? You're muted.
Perfect, perfect.
No, it's good. Ah, amazing. Okay, I'm glad. Okay, cool. Okay. So, where was I? Yes. So, if you are in a numerical analysis, what you want to do is you have a differential operator, I call it D, and you want to find the function U such that D of U is equal to 0. So you can think of D like a Laplace operator, for instance. You can think of it as a transport operator. So differential in du dt plus A times du dx is equal to 0. You can think of it as something like that. Another task that is quite well known is supervised learning. So you have a set of data, xk, yk, and you try to find the function u such that u of xk is equal to yk for every k. And so in these two tasks, as you can see, the goal is to find the function. And so this function, theoretically at least, it lives in an infinite dimensional space. It lives in a space with different dimension infinity. For instance, you can think of it as the L2 space of functions. However, since we are, what we want to do is, we cannot solve these problems exactly, so we will need to find approximations of the function u, for instance. So, because we want to do that on a computer and we don't have infinite memory, necessarily we have to approximate the function u inside a finite dimensional function space, which is a subset of your Hilbert space H. So, in the first part of this talk, what I will say is I know a function u, and I want to find a way of approximating this function u inside a finite dimensional function space. Okay, and of course, the whole goal of this will be how to find the good function space in order to provide a good approximation of u. All right, let us start with linear approximation space, which is a notion which all of you are probably quite familiar with if you have just done a bit of numerical analysis. Maybe you have not seen this notion in this specific way, but you already know what that is. So I consider omega, which is a subset of Rd. Okay, so we have a space domain in dimension d. D is equal to 1, 2, 3, or even more. We have an infinite dimensional space H, and we have a function u that lives in this infinite dimensional space H. And we define a linear approximation space, Vn, as the span of some basis functions. So you define n basis functions, which are some functions that are well defined. You define basis functions, it gives you your space, and then every element of your space is, of course, given as a linear combination of these basis functions. So for every element of the space Vn, you have the existence of a vector theta, so a vector theta of R capital N, such that u theta of x, which is an element of Vn, is the sum of theta j times phi j of x. So here I am just saying that Vn is a vector space, is a linear space, a subset of H. So in this case, the vector theta will be called the degrees of freedom of the approximation space of the solution u theta. So a first example that I can give is the example of the finite volume method. In the finite volume method, you take your domain omega, you mesh it, so you introduce a mesh, a partition of the domain omega into cells, and you define your basis functions as the indicator functions of each cell. So each phi j is the indicator function of the cell j. And that is, each phi j is equal to 0 outside of the cell omega j and equal to 1 inside of the cell omega j. And that is one specific case of basis functions, which will give you the finite volume method. And so, of course, now the goal is that given the basis functions, given the phi j's, what I want to do is I want to find the best approximation of my function u of my infinite dimensional function u by a function u theta, which is in Vn, so which is in the span of the phi j's. And so that is to say, I want to find the degrees of freedom theta. So I want to find the best theta possible, the best possible theta to represent u by u theta in Vn. And so here we can just do a bit of linear algebra. Because actually you see that u, which is a function in the infinite dimensional space, you can represent it by a function in the finite dimensional space by just performing an orthogonal projection. So you will orthogonally project your function u onto the vector space Vn. To do that, you just draw here this line, which is u minus u theta. And so you will impose that u minus u theta should be orthogonal to Vn. And that is exactly so an orthogonal projection. And that is exactly what we actually do to find the theta. So we find u theta such that u minus u theta is in Vn. Another possibility of seeing that is to find theta such that the distance between u and u theta is minimized. It's this formula here, and it gives you exactly the same formulation as the orthogonal projection. So in the end, what you are looking for is u theta in Vn, such that for every v, for every function in your space Vn, you have that u minus u theta inner product with v is 0. So you have that u minus u theta is orthogonal to v. But since v lives in Vn, v is in the span of the phi j's. And so because v is in the span of the phi j's, it means that u minus u theta should be orthogonal to every basis function phi. So if you rewrite that, it means that for every I between 1 and n, so for every phi I want, and also, sorry, you write the u theta as a sum of theta j phi j. Well, you have that the sum of theta j times the inner product between phi I and phi j is equal to the inner product between u and phi I. And in this case, what you obtain is a linear system, m times theta is equal to u, where m is a mass matrix, which is given by the inner product between the two basis functions, and the right-hand side is the inner product between the function that you're trying to approximate, and phi I. So here, what I have shown you is what we call the Galerkin method, and the Galerkin method is exactly at the basis of what you have when you do finite elements. If you do finite volumes, if you do finite volumes, if you discontinuous Galerkin methods, everything is encompassed in that. But you have a generalization of this method, which is also quite used, which is the Petrov-Galerkin method. So in the Petrov-Galerkin method, instead of projecting orthogonally to Vn, you introduce a new vector space, Wm, and I emphasize that here the dimension of Wm is, well, m, which is possibly different from n. Okay, so you have two different vector spaces with possibly two different dimensions. And so, because in this case, you want the residual u minus u theta to be orthogonal to every w in your what is called the test space Wm. And so in this case, so of course it's just a generalization, because if Vn is equal to Wm, then you recover the case that we had before. And otherwise, it is what is called in linear algebra, it's called an oblique projection. And so in this case, you are looking for the n degrees of freedom, such that for every basis function inside of Wm, so for I between 1 and m, you have this equality here. And so you have a linear system, which is this times k theta is equal to u. The u is almost the same, except that you replaced phi by psi. And the k is, instead of having inner product between phi j and phi I, you have the inner product between phi j and psi I. But what you can see is that if n is different than m, this linear system will be rectangular. So it will be either overdetermined or underdetermined. And so because of that, instead of just solving the linear system, you will actually solve it in a least squares way. So you will find theta, which is the minimizer of the residual here, k theta minus u. So you will find the theta which minimizes the norm of k theta minus u. Okay, so that is what we do in classical methods. Maybe it's not necessarily the way you're used to seeing these things, but if you have done some finite elements or something like that, it's something that should be at least a bit familiar. Now I will just give you an example because it is important, I think. So the example is the finite volume method. So I go back to the finite volume method. In this case, you remember that I have my domain omega and I split it, I partition it into cells. I partition it into n cells, which are sigma j. Then the basis functions are the indicator functions, and I can actually compute exactly the right-hand side of the matrix. So the right-hand side is the L2 inner product between u and phi, so it's the integral of u times phi. But phi is the indicator function of the cell omega I, so ui is just the integral over omega I of u. In the same way, you can calculate the matrix M. The matrix M is the inner product between two different indicator functions, which is 0 if it's not the same indicator functions because they have different supports. And otherwise, it is just the volume of the cell omega I. And so it means that your degrees of freedom are just the averages of your functions that you're trying to approximate on every cell. And so this is the full representation, which okay, I'm not reading it because it's too long. But what I mean is that if you want, so if you are given a function which is piecewise constant, and you want to approximate a non-piecewise constant function by a piecewise constant function, it means that the approximation, the pieces, the piecewise constants, are just the average of your function on every cell, which makes sense. And if you have already practiced a bit the finite volume method, this is exactly what you do to initialize your finite volume method. You compute the average of the initial condition on every cell. Another example, which I will come back to a bit later, is Gaussian radial basis functions. In this case, you define some centers Cj, which live in omega, and you define a variance sigma. So you can see on the drawing here, you have a couple of different functions which are in brown here. Each have a center and each have the same variance. Okay, so you have evenly spaced centers and you have the same variance for every function. And so in this case, you define your u theta as a linear combination of all of these Gaussian bumps. Okay, and you have the sum of the theta j times each Gaussian bump here. So it's another possibility to represent, to obtain a linear approximation space. Okay, so now that we have these two examples, what I can tell you is that we have a very, very good, very important property in the linear case, is that we have convergence. So it is a very good advantage. It is really why we have been using this method extensively for the last 50 years, because generally, for some p strictly positive, what you can prove is that the error between u and u theta in your L2 norm is O of n to the power of minus p over d with this dimension. So it means that whenever you increase n, necessarily you decrease the error, and you know how much the error decreases. And it's something, if you have practiced a bit some numerical method, it's something you are used to, right? You refine the mesh, so you increase the number of degrees of freedom, you refine the mesh, well, necessarily you have a better solution. Of course, it's what we expect. But the problem is this little guy, this little d here. And actually, if you reverse this estimate, if you want to reach an error target epsilon, so you here you say epsilon is equal to O of this guy, you reverse everything, and you see that the number of degrees of freedom that you
Sorry, the mic is mute.
We couldn't hear you again, Victor. Hello, Victor. I guess it's out. Hello, Victor.
Send him a chat. Send him a chat.
Yes, yes, yes. Hello, Victor. Wow.
Headset.
Yes, we lost you at some point.
Okay. When do you think you lost me?
Maybe you go backwards. Yes, we lost you at, yes, yeah.
Here.
No, at the advantages.
Ah, here. Okay. So I redo this slide. Okay.
Thank you, yeah.
No, no worries, no worries. I'm sorry about that. I think my somehow my headset died. I don't know why. I will try to please write in the chat because I think I will see the chat if there is an issue. Okay, so what I was saying is that when you have a linear approximation space, what you know is that the error between u and u theta, so you are approximating u with u theta, which lives in Vienne. The error between u and u theta is an O of n to some power. And so this means that as the number of degrees of freedom increases, the error decreases, which is something you have experienced if you have seen, if you have used yourself like a finite volume method or something. If you increase the number of cells in your mesh, well, necessarily you decrease your error. You're used to that. You know that it is the case. But the problem is this D here. So if you try to reverse this estimate here, you are given an error target epsilon, and you want to compute how many DOFs you need to achieve this error target. You reverse the estimate, and of course, this n to the power of minus p over d will become an epsilon to the power of minus d over p. And so that means that when d increases, so when the dimension of your domain increases, the number of DOFs, the number of required cells in your mesh will increase exponentially. And it means that, okay, if you have, for instance, if you take a scheme with 100 cells in your mesh in 1D, you can achieve an error of, I don't know, 10 to the minus 2 randomly. But if you want to achieve an error of 10 to the minus 2 in 3D, you will need 100 cells bi-direction, 100, 100, 100, 100. And so this means that you will need 100 cube, which is much, much more than just 100. And so you see that to reach an error target, you really need to increase the number of DOFs exponentially with the dimension. And this is bad. This is very, very bad. Because what we are interested in can be PDEs in 6D. Because if you do plasma, you will have to solve PDEs in 6D. And in 6D, so you want to avoid this curse of dimensionality. And to do that, one possibility is to move to nonlinear approximation spaces. So why nonlinear approximation spaces? I have this picture that I stole from some paper here, which is quite nice, I think. Is that if you focus on the picture on the left, you see that if you want to approximate the trajectory of the points in black, if you want to use a linear space, well, the best fitting linear vector space is the plane. So here it's in R2, right? So you want to approximate a trajectory in R3 using something in R2. The best fitting plane in a subset of R2 is this blue guy. And you see that the projection of the black dots on the blue plane is quite bad because, of course, the blue plane is not really fitting the black dots. However, if you focus at the right picture, what you see here is a quadratic manifold. So a quadratic manifold, it's just a surface in R3. So a surface in R3 is given by 2 degrees of freedom. Okay, this surface is given by 2 degrees of freedom, and as you can see, the black dots lie almost perfectly on the surface. And so it means that with the same number of degrees of freedom, so here you have 2 degrees of freedom that give you your plane. Here you have 2 degrees of freedom that define your quadratic manifold. So with the same number of degrees of freedom, you are able to get a much better approximation of your trajectory compared to the linear case. Okay, so this is exactly why we turn to nonlinear subspaces. Okay, so just to give a bit more, just to give an example right away of what could be a nonlinear space for function approximation, recall the Gaussian RBFs. So what I told you just before is that you take some fixed centers and the fixed variance for every Gaussian bump that you see here. And you take u theta as the linear combination of all of these Gaussian bumps. So this is a case where you have a linear approximation space. But okay, why are the centers fixed and why are the variances all the same? You could imagine having a linear combination, but of Gaussian bumps with different centers, so not evenly spaced centers, and with different variances. It's a possibility. There is no problem of defining that. But in this case, it means that you don't need only to find the theta j's, but you need to find the alpha j's, which will be the coefficients in front of your Gaussians. You also need to find the best centers and the best variances to best represent your data, to best represent your function u. And so you see that because the centers and the variances are inside of the exponential, so by definition, you see that you do not have the same kind of problem. Finding the alphas, if C and the sigmas are fixed, finding the alphas is just a linear problem, whereas finding alpha, C, and theta and omega and sigma, is a non-linear problem because the C and the omega sigmas are inside of the exponential. Okay, so just to formalize that a little bit, first I have an example. So here you can see on the left the approximation of a function using linear RBFs, and on the right the approximation of a function using nonlinear RBFs. So on the left, you see that all of the bases, all of the Gaussian bumps, they are really evenly spaced. They have all the same variance, and when you add them up, you obtain a good approximation of the reference solution, which is here in orange versus the reference solution in black. If you go to the nonlinear space, well, okay, here every Gaussian is all over the place. You do not have a nice ordered thing like that, but you only have 20 Gaussian bumps with variable centers and variable variances. You can see that here you have a very wide Gaussian, the blue one, whereas, for instance, this red one is very, very tiny. And it's even worse where you go to the approximation of a discontinuous function, where here you can see an extremely spiky Gaussian close to the discontinuity. So this is just an example to show you that you can achieve a good approximation in nonlinear spaces, and that can also work. So now what I want to show you is actually how you can find the approximation in the nonlinear space. So first, a definition. What is a nonlinear approximation space? So a nonlinear space, which I'll also call Vn, but curly V, is defined as by a nonlinear function n. So I give you any nonlinear function n, which goes from omega cross Rn to R, which takes as inputs x as well as the degrees of freedom. And this defines my nonlinear approximation space. So at this level, you will tell me, okay, it's extremely general definition. This is on purpose, okay? It's just to say that I have functions which depend on x and on the parameters, on the DOFs theta, and I need to determine the thetas such that this nonlinear function here is a good approximation of my function u. So to do that in practice, what do? Well, we do an oblique projection. So exactly the thing that I told you before. But we do an oblique projection on a specific space Wm. And actually the space Wm that we choose is the span of the Dirac deltas located at some points which are drawn in, which are randomly sampled in omega. So you sample m points in omega. You define the test space Wm as the span of the Dirac deltas at the collocation points, and you project the residual u minus u theta onto Wm. And so it means that for every I between 1 and m, you want that u minus u theta is orthogonal to the Dirac delta at xi. So once again, you have something which is, so it's non-linear, so it's not a matrix, but still you have n, which is possibly different from m. So you have a minimization problem. And when you just expand this guy, it means that you are just evaluating u minus u theta at xi. And so you want theta to minimize the sum of u of xi minus u theta of xi for all the i's between 1 and m. So you want to minimize the difference between u and u theta at every collocation point. And so if you have enough collocation points, you see that, of course, you will converge. You will have u which is equal to u theta for every point in omega. So what is good and what is bad here? The very good thing is that you don't have a mesh. It's very good that you don't have a mesh because you just need to sample the domain to obtain the collocation points. You just need to somehow be able to define some collocation points. And I think you will agree that usually it's easier to just randomly sample points inside of a domain compared to meshing the domain. Where meshing, you can have some issues if you have some corners of whatever. Another very good very good thing is that you can reach higher dimensions, thanks to the property that I showed you before, that with fewer degrees of freedom, you are able, with a curved space, to better represent some data. But, and it is a big but, the problem is that this minimization problem is actually quite hard. It's a non-quadratic, a non-convex, non-linear optimization problem. So you do not have a linear system. It does not lead to a linear system. And you need to really understand how to solve this minimization problem to obtain the DOFs with good precision. So to do that, we look a bit at the sources of error that we make when we approximate our function u in our space Vn. So what we want to minimize is the so-called approximation error, u minus u theta in at the continuous level, so in the full Hilbert space H. So once again, think of it as L2. So what you want is that theta minimizes this error here, and so you have one error here. Okay, how well can u theta minimize, approximate u in the best possible circumstances? So you are just saying, okay, I really want to say, how can my u theta be a good approximation of u? Do I have enough degrees of freedom? Do I have is the dimension of my nonlinear space enough to approximate u? So this gives you one source of error. How well can my nonlinear space approximate my function u, approximate my Hilbert space H? Then you have two other sources of error. You have one source which comes from the fact that actually you are approximating the integral because you are replacing this with Monte Carlo. It's not important, but you're replacing this with a Monte Carlo estimation. So this leads to what is called an integration error because you are replacing the integral here by a sum. And because you are not able to actually solve the minimization problem exactly, thus you introduce an optimization error, which which tells you how well you are able to actually approximate the minimization of your target function. So to sum up, you have three sources of error: an approximation error, how good is your finite dimensional space, an integration error, and an optimization error. In linear methods, usually the approximation error will dominate, because if you think of, for instance, finite elements, so if you do, for instance, P2 finite elements, you will readily say that P2 finite elements will give you, given by a second the polynomials of degree 2, will give you a better approximation than P1 finite elements, which are given by polynomials of degree 1. You will be able to better represent a function in L2 using quadratic polynomials compared to linear polynomials. And so usually this is the error that dominates. Then the integration error is also important because it's how you approximate your integrals. But in linear methods, usually the optimization error is 0 because you can exactly solve the linear system that you are presented with. Or you have an iterative procedure, and in which case it's the error of the iterative procedure, but usually it's almost 0. But for nonlinear methods, as we will see in the next slide, the more complicated error, the biggest error is the optimization error. And so it becomes extremely important to have a good optimization algorithm. Otherwise, you will have a very, very bad value for your DOFs, even though you could find better DOFs with a better optimization algorithm.
Hello, Victor. Hello, Victor. We lost you again. Can you all hear?
No, no one is hearing him.
Okay.
Okay, can you hear me?
Yeah, we can hear you now.
Wait,
We lost
no,
you.
wait, one sec. It's my fault. Okay. Now can you hear me?
Yeah, we can hear you now.
Okay, somehow I can't hear you. I don't know why. Yes, no, okay. It's my sorry. Up. I need to add some sounds. Come on. Okay. And output speakers, output up. Can you just speak just to be sure?
Can you hear me?
Okay, perfect. I can
Good.
hear you now. Okay.
Okay.
Okay, so I hope you didn't lose too much.
Yeah, just this slide.
Okay, just all the whole of the slide you lost.
Yes.
Okay. So as you can see on the left, so okay. Okay, so what I'm comparing is the approximation with 60 degrees of freedom on the left and 192 on the right. So purposefully, I choose a small number of degrees of freedom. Usually when you do machine learning, you have a large number of degrees of freedom, you have a large number of weights and biases. And I just want to show you that you can get very good approximations using very few degrees of freedom. So you can here see the chart of the error between nu minus u theta compared to, with respect to the number of epochs, which is just the number of iterations of the nonlinear optimization procedure. And as you can see, the red optimization algorithm is only able to give you an error of 10 to the minus 3-ish, whereas the blue optimization algorithm goes down to 10 to the minus 9, which is actually quite good. For those of you who have dabbled a bit in machine learning, maybe you know the Adam optimizer. So Adam is a first order optimizer, which is so a nonlinear optimization algorithm, which is widely used in machine learning, which has good properties for machine learning tasks, but quite bad properties for function approximation tasks. And so as you can see, Adam is compared to the blue one, which is called natural gradient, Adam is really, really bad in our case. So as you can see, is that it is crucial. I mean, the efficiency of the optimization algorithm is really crucial to obtain a good accuracy.
Yeah.
Okay, so I can just okay, I will show this to you very quickly. So as you can see, so here I'm showing top left finite volume, top right linear RBFs. So you see that compared to the increase of the number of degrees of freedom, you have a decrease of the error. You have a predictable decrease of the error, which is to the power n to the power of minus d for the finite volume, and something spectral for the RBFs, but you still have a predictable decrease. Whereas when you go to nonlinear spaces, so for RBFs it doesn't work so well, but for MLPs, which are a type of fully connected neural network, you can see that the error diminishes by quite nicely when you increase the number of degrees of freedom. And as you can see, this error does not really depend on the dimension. You see that even for dimension 5, which is in blue, you have almost the same level of error compared to dimension 4, even with the same number of degrees of freedom. So it means that compared to the linear case, you have a very, very good, I mean, you're really able to almost remove the curse of dimensionality, at least when you go to reasonable dimensions, not 100, but for d equals 5, it worked quite well. And so here you see you arrive at an error of 10 to the minus 5 with 1000 DOFs, whereas for the RBFs you only get 10 to the minus 2 with 1 million DOFs. So it's really quite a nice improvement. Okay, so just to recap, the advantages of nonlinear spaces is that you have density theorems, so you're happy because you know that you are dense. You have an error which is less dependent on the dimension. It's not completely independent, but it depends less than for linear methods. And you don't need a mesh, which is nice. However, the drawbacks are also quite bad because you don't have convergence rates. So despite the fact that your nonlinear spaces are dense in L2, basically, you do not have convergence, and so you do not know how the error diminishes as the DOFs increase. And also, it is very difficult to solve the optimization problem because it has many bad properties. So in spite of these drawbacks, it is quite interesting to look at these methods to solve PDEs. And actually, this long introduction using function approximation is quite easily extendable to the PDE case. And that is what I will talk about right now, stationary PDEs. So let us consider an elliptic problem. I don't talk about boundary conditions for now. So an elliptic problem, which is a differential operator applied to u, is equal to f. So you can think of it as, for instance, the prototypical problem would be minus Laplacian of u is equal to f. So a Poisson problem. And in a very similar way, you will define a linear approximation space by saying, okay, it's the space of functions which are d of u theta, and these functions are u theta are given as the span of as the linear combination of some basis functions. And so what we have done in the functional approximation extends directly to the PDE case, because you can do the Petrov-Galerkin projection, so you can do the oblique projection. So you want to find f theta in Vn, such that for every w in your test space, you have f minus f theta, which is orthogonal to w. And so for every psi in your Wm space, you have that f minus d of u theta is orthogonal to psi. And so this is exactly what you solve in the finite element case. Because if you have, for instance, the Galerkin method, in the finite elements, you solve exactly that, but you have, for instance, here, once again, think of the minus Laplacian of u. So you have the sum of theta j's times minus Laplacian of phi j's, and you have the integral of Laplacian of phi j times phi I, which you replace by integral of gradient of phi j times gradient of phi I, and here you have your mass matrix, your usual mass matrix in the finite elements. You can also define a collocation method if you have a Wm given as the span of some Dirac deltas, and in this case you will say that the residual of the PDE should be equal to 0 at every collocation point. So it's really everything that we have done for function approximation is directly translated to PDEs. And it's also exactly the same for in the case of nonlinear methods. So in the case of nonlinear methods, you also use an oblique projection. You also define a test space, which is the span of your collocation points. But this time, what you project onto the test space is not u minus u theta, because you do not have u, but you project the residual of the PDE. So you project f minus d of u theta, f minus your differential operator applied to u theta. And so this means that theta will be the minimizer of this quantity here. And this quantity is the residual of the PDE evaluated at the collocation points. And so you can readily see that, imagine, just for the sake of argument, that you have an infinite number of collocation points. So this means that for every x in omega, you have d of u theta of x minus f, which is equal to 0. And so it means that u theta satisfies d of u theta is equal to f for every x. And so if you have an infinite number of collocation points, then you have an exact solution to your PDE, which is good. Of course, it is not reachable in practice, but it's the idea. And actually, all of that exactly leads to what is called in the literature physics-informed neural networks. It's maybe something that you have heard of. It's based on the work by Recherche and co-authors, which was published in 2019 and has roots in the late 90s as well. But physics-informed neural networks are simply a Petrov-Galerkin projection onto a test space made of collocation points and with a nonlinear approximation space. So this maybe can alleviate a bit of the black box feeling that one can have when one thinks of numerical methods for PDEs with neural networks. It's just so PINs, physics-informed neural networks, are just a specific kind of numerical method. I can show you a few examples. Did I miss? Okay, well, I can show you a couple of examples. Once again, I want to compare Adam to natural gradients. So on top, what you see are the results. So it's a Poisson problem minus Laplacian of u is equal to f. So I have two parameters inside of my problem, which I treat as a spatial variable. So I can see the full problem as a 4-dimensional problem. And so what you see is that here with Adam, you have an approximation which is okay, but with natural gradient, you see that the residual, the error, is of the order of 10 to the minus 6 for the whole 4D space, which is quite nice, and it's something that is hard to reach, especially in 4D, using standard finite elements. But it emphasizes that you really need a good optimization to obtain a good accuracy. Otherwise, you are completely lost. Okay, so once again, advantages are that you don't need a large number of degrees of freedom to reach a good accuracy, even when you have when you are in high dimensions. It could be easier to deal with complex domains because you don't have a mesh, but the cost per degree of freedom is much higher than with linear methods. And once again, you do not have any good convergence results. And in practice, what you see is that adding degrees of freedom, it doesn't necessarily help to reduce the error. And sometimes you, as you saw, sorry, I don't like to do that, but as you saw here, for instance, we, in the blue case, we multiplied by 2 the number of doffs, and the error increased. So it's really not something that you're used to in classical methods. In classical methods, you multiply by 2 the number of mesh cells, the error doesn't decrease. It would be impossible, okay? So this is a behavior you can see with nonlinear methods. So what's the work that we have been doing in my team is to try to improve the accuracy of pins and to improve the error constant of linear methods by trying to hybridize the two. So by trying to get the best of both worlds. So Because of the interruptions, it's a bit late. So I don't know if I can talk about the next part. I can be a bit quick, but because it's a bit late, I don't know if it makes sense to start now. I guess I can.
Yeah, continue.
Continue? Okay, cool.
Okay.
So what I can tell you about is work that we did that was published in 2026 in N2AN. And once again, it's the work that is done in the context of the PhD thesis of Frédéric Lecourtier. And so we try to enrich finite element approximation spaces with neural networks. So the motivation is the following. As I told you, nonlinear approximation spaces are powerful, but they do not converge. Conversely, linear approximation spaces, you have, if you do finite elements, for instance, you have convergence, but you do not have but you have a curse of dimensionality. Can you combine the two? Well, what we propose is a two-step hybrid method with an offline phase where on the offline phase, you train a neural network, which will approximate a large family of solutions to your PDE. And then in the online phase, so the offline phase, you do it once and for all, and then it's done, and you set it aside. And in the online phase, it's something that you redo at every new simulation. You will use this network to correct the CG approximation space. So it means that you will be able to run the finite elements, so continuous Galerkin finite elements, I will use the two interchangeably. You will be able to run the CG method on the coarse grid. So how to do that? Well, I recall that the classical FEM, so the finite element CG method, it relies on an approximation space, a linear approximation space with piecewise polynomial basis functions. So you have the phi j's, which are piecewise polynomial functions. Usually they can be defined, for instance, as hat functions centered at the nodes of your mesh. And so the approximation is u theta, such that u theta is a linear combination of these hat functions, or these quadratic polynomial functions, or whatever. When you want to actually find the DOFs, what you do is you rewrite your PDE as a variational problem. So you define a bilinear form and a linear form, and you recast d of u is equal to f as this particular variational problem, which then you discretize, okay? And discretizing this variational problem gives you a linear system that you solve to get the approximation un of u. So this is classical CG, classical finite elements. If you don't know classical finite elements, it's completely okay. I just want to emphasize that usually what we do to solve this problem is to solve a linear system. So now, how to modify this space, how to enrich this space? Well, we make an assumption, okay? At this level, we make an assumption. We say that we know some prior information, so it should be in H, sorry. We know some prior information, which I call U star, and it is supposed to be an approximation, any kind of approximation of the exact solution of your elliptic problem. One possibility to get this U star is to train a pin during the offline phase and to give you some U star. But it's only a possibility, and at this level, I'm just saying I suppose I know some information, I know some function which is an approximation of my true solution. And so what I propose is to modify the CG approximation space by adding this prior. And so it means that I define a space Vn plus, which is U star plus Vn. And so it's no longer a linear space, but it's an affine space. Okay, it's not a vector space, but an affine space. And it is the space of functions which are defined by U star plus eta theta, where eta theta itself is an element of my linear space. So this eta is a piecewise polynomial function. So you can see eta as a piecewise polynomial correction to the prior information. Okay, And so this is another definition of the enriched space. So every element is, so u theta plus of x is equal to u star of x plus a polynomial correction that needs to be determined. So it means that you have an enriched space which is affine, as I said, but it still leads to linear systems despite this u star. Indeed, if you just redo the full, if you redo the derivation of the linear system, just to give the basis is that in a non-enriched method, I want to find un in Vn such that A of un Vn is equal to L of Vn for every Vn in my space Vn. Okay, it's a bit strange to have many Vn's, but okay, I should say capital Vn. Sorry. And in the enriched method, it's a Petrov-Galerkin way. And so we try to, for every Vn in capital Vn, we try to find u theta plus in Vn plus, such that you have this equality here. But u theta plus is u star plus eta. So it means that because A is linear, it just means that we want to find eta such that A of eta and V is equal to L of V minus A of u star and V. And so you see that compared to the first non-enriched problem, the enriched problem is not so different, yes, because you have the same bilinear form, so you will have the same matrix, but you will have a bit of a different right-hand side. The right-hand side incorporates the prior information. So thanks to this formulation, it's actually very easy to write an error formulation. So we can do a full error analysis, exactly like we do in finite elements. And we can prove that the difference between u and u theta in the enriched space is smaller than a constant C gain, which I will discuss just after, times the classical error of the CG method. Okay, so I know that I have the exact same error as the classical CG method times some constant. And what is this constant? It is this guy here. So it's the HQ plus 1 semi-norm with, if I have a Q or a scheme of order Q, so with PQ polynomials. So it's the Q plus 1 semi-norm, HQ plus 1 semi-norm of U minus U star over the Q plus 1 semi-norm of U. So just to say what it actually means, is that if the Q plus 1th derivative of U star is a good approximation of the Q plus 1th derivative of U, it means that the top thing here vanishes, or at least is very small, and so your constant here is very small. And so if you have a very small constant here, it means that by using the enriched space, you are able to have the classical CG error with the convergence, okay? So you have the same convergence rates, but with a smaller error constant. And so you are very happy because you have managed to improve, to enrich the classical finite element method using your prior to retain the same order of accuracy, but decreasing the error. And this is quite nice. And actually, the remark here is that u theta, as I said, must be a good approximation of the derivative of u. And this is why we use pins, because pins inherently use the information from the derivatives. So just to wrap up, we have proposed a two-step hybrid method. In the offline phase, so something you do only once, you train a pin, which is u star to approximate a family of solutions. And in the online phase, what you do is you compute eta in your, you compute a piecewise polynomial function eta, which will be used to correct u star and to give you an approximation u theta plus, which is, let's say, a better approximation than the classical CG one. I have a few numerical experiments. I can be quite quick on that. Okay, maybe I can show you this one. So here you have the exact solution. Okay, it's quite oscillatory. Here you have the solution given by finite elements. And here you have the solution given by the prior plus polynomial correction. So actually, I don't have the prior displayed, but it would look with the I-norm, it would look like a solution. And you see that basically the correction is this guy. So the prior is, the additive solution is U star plus this guy here. And you see that this guy here is not very hard to approximate. So the finite element method is able to approximate this pH plus with quite a good accuracy. And so you can see that also the error in FEM is much larger than the error in the enriched space. We can show that as well on convergence curves. So the blue curves, just at least focus on the blue curves for the moment. The blue curves correspond to P1 finite elements. So the solid lines are the classical P1 finite elements, and the dashed lines are the enriched P1 finite elements. And so you see that you gain almost 2 orders of magnitude in terms of error. So you have the same convergence rates, but a much lower error. And yeah, this is exactly the same observation for the P2 and P3, so third and fourth order finite element schemes. This I will skip. And yes, I also want to show you, so this was quite a simple problem, and I just want to show you a problem which is a bit more complicated. So it's Poisson problem, so it's still minus Laplacian of u is equal to f, but this time the domain is a donut. Instead of being a square, the domain is a donut, and outside of the donut you have Dirichlet boundary condition, and inside of the donut you have Robin boundary conditions. So you have mixed boundary conditions, which can be quite hard to deal with FEM. So with the I-norm, you don't really see any difference, but when you look actually at the error, you see that the error given by the finite element method is quite large, especially close to the inner part of the donuts, whereas with the enriched method, you manage to reduce the error. You have the same observation as before. You have the same rate of convergence, but a better error constant. So you have the same slope, but a lower value of the error. And so finally, what I can show you is the same experiment as the first one, but in 3D. So I don't have plots here, I just have the errors. And so as you can see, so here Frédéric only did it with P1 because it took too long with P2 or P3. So you can see fairly easily that you have the same, once again, rate of convergence, but a much lower error using the enriched space. And so you see that the gain is usually about 100. So you gain a factor of 100 in the error. Yes, so it can be interesting to just check because in all of that I have not told you anything about what it costs to actually train the pin, to actually find U star. So to find U star, to train the pin, it takes about 700 seconds, okay? And the cost of one CG simulation on a fine grid is about 40 seconds. So you can see that if I only want to do one CG simulation on a fine grid, it doesn't make sense to train a pin to do that. It really doesn't make sense. So where everything becomes interesting is that if you want to do many CG simulations, because thanks to your thanks to the enriched space, you are able to use a much coarser mesh than to reach the same level of error. Then you can see that the online cost, so the simulation cost of the enriched CG formulation is extremely small, it's almost negligible. And so you see that with only 18 CG simulations, 18 coarse simulations, I am plus the training of the pin, I am faster than running 18 fine CG simulations. Okay, and so just to conclude, we have introduced a unified framework for approximating functions in linear and nonlinear spaces. We have shown you how to extend that to approximate solutions to stationary PDEs, to elliptic PDEs, so The time-dependent extension also works, but I didn't have time to present that. And the extension I want to say is very straightforward to go from function approximation to PDE approximation. And I have shown you a hybrid method between CG and pins. In terms of perspectives, what we want to do is to learn basis in the discontinuous Galerkin framework and tackle time-dependent problems. And we want to extend this CG thing to nonlinear problems. What I want to say also, I want to give some advertisements on our library that we are developing right now, which is called Simba, like the lion. And it's Python plus PyTorch plus JAX library, which includes many scientific machine learning methods for PDEs, so pins, time-discrete pins, etc. And it's open source, so you can check it out if you're interested. And I thank you again for your attention, and I apologize once again for the technical issues during this talk, which are completely on my part.
Thank you very much for your wonderful presentation, Victor. Really, I found the lectures very interesting, and I'm sure that our students and researchers listening to you would have found very new things and new grounds to. And I know this will not come without questions. So if you have, maybe we take like two. We have had a very long day today, so if you can take like maybe 2 questions.
Yeah.
Victor will be ready to answer your questions. Any questions from the participants? Do you have any question? Any question?
Okay, yes, question.
Yes, please go ahead.
Okay, thank you very much, Victor, for your wonderful presentation.
Please, your name first. Your name before I ask you a question, please.
Yeah, my name is Dr. Chinedu Migwe from Port Harcourt.
My guy.
Okay, so thank you very much, Victor, for your presentation. It's quite interesting. I'm always fascinated with pins and all those stuff. So I'm trying to, can you throw more light on the offline training? So how are you training the solution of the PDE?
It's a good, so okay, it's a good question. I did not say anything about that. Thank you for asking. So basically, so for instance, imagine that you are trying to solve this PDE here. Okay, so this is just minus Laplacian of u is equal to f. So what you do is you apply exactly, sorry, I'm going back. You apply exactly this methodology here. Okay, so you just train a pin. You just take no, you don't have exactly to think of it in the Petrov Galerkin way. You just say, okay, I know that I want to train a pin to give me an approximation of the solution to minus Laplacian of u is equal to f. And so how do I train it specifically? Well, actually, what we observed, it was quite interesting. What we observed is that it doesn't really, I mean, of course, if we train it better, then we will have a lower error. So, sorry, I'm going back. What I want to minimize basically is this error here, the u minus u star in the q plus 1's derivative of u minus u star. So basically, I train a pin. If I train it well, which means if I have a good representation of the q plus 1 derivative, then I will have a low error constant, and so I will be happy. And if I train the pin, if I don't train the pin well enough, then I will have a constant which is higher. But it's also something you can, and when I say well enough, there is no magic recipe. If you add degrees of freedom, so you add layers or you add weights and biases in your neural network, possibly you will have a better approximation. If you do more epochs, if you do more iterations of your nonlinear solver, you will probably have a better solution. But what I want to say is that in this case, if you choose not to train the pin so well, you can choose that, it's your right, and then the offline cost will be quite low, but you will probably still have a gain constant which is smaller than 1. So you will already improve the FEM, the classical CG, even by training the pin, by not training the pin too much. So yes. So now I don't think so in terms of specificity, how many epochs, what kind of layers, etc. I'm afraid I cannot specifically answer that because I didn't do the experiments. Our PhD student Frédéric did the experiments. So, but she wrote everything in the paper. So if you're interested in the specific details, I can put a link to the paper on the chat. But basically, to answer your question, to train the prior, to train the U star, it's a pin, and you train it however you want.
Thank you. So Victor, so maybe tomorrow I'll send you an email for you to send me the slides and maybe paper. Maybe you send some papers that are useful to this talk.
Yes.
Okay. All right. Okay. So any other question before we leave? Any other question? Final question.
Sorry, I have a question, sir.
Okay, please go. Please ask a question. Sir.
My name is Samuel. I'm from Metro. That's it. So while reading your background, I had something like you are in numerical machine learning, and I really don't know what that means. Please, if you can explain that.
Numerical.
I'm sorry, I didn't quite get that.
While reading your background, I had something that you are in numerical machine learning. I don't know what complete that, but then I don't really know what that means. Is that a field? Something
he's trying to ask numerical machine learning. Maybe he said while reading your bio sketch, he saw a place where they wrote numerical. It's scientific machine learning you meant?
Yeah, scientific machine learning. So a definition of scientific machine learning, you mean? Or yes. Okay. So basically, so there are many different definitions of scientific machine learning. In some cases, one could argue that this is scientific machine learning because basically scientific machine learning means using machine learning tools to solve PDEs, to give numerical approximation of PDEs. So what machine learning tools? It can be neural networks, in which case you obtain something like pins or some variants of pins. It can be neural operators, in which case you can use you can obtain like green nets and stuff like that. So it can be a whole slew of different things. And if you're interested, so for me, more specifically, where this becomes interesting, in my opinion, but it's only my opinion and it's not necessarily the opinion of everybody, but in my opinion, where this becomes very interesting in a mathematical sense, is where you try to combine the two somehow, and you try to somehow retain the convergence of classical methods while getting the nice properties of the machine learning stuff. And this is also a part of machine learning. So hybridizing classical and machine learning methods is also part of scientific machine learning. And so yeah, basically, if I want to say it in a few words, scientific machine learning is solving PDEs with tools, any tools from machine learning, basically. And so doing scientific computing with machine learning.
Very much for the clarification.
Yeah.
Thank you very much, Sam.
Okay, thank you very much. And also to help Victor advertise, I have put on the chat box
thank you.
The website to his group's website on scientific learning, simba.org. So if you're interested, you could just click on that link to just see what is happening there and find.
Yeah, it's our code, so it will send you to the documentation of our open source package. If you're interested in checking that out, it's an open source package in which you can use pins to solve equations and stuff. So if you're interested in that, you can use it.
Thank you very much. Okay, so maybe I just I don't know if Professor Mebin is around. I don't know if he's still here with us. Okay, I think he's gone. Okay, is Professor Adekunle still here with us? I don't know. Okay. So at this point, I think we should just, I think it's a good time to go.
Okay.
So
Yes, so
yeah, it's a good time to go. I think we have spent so much time, and
yes,
I hope we'll all be available for the next edition in June. In June, we'll be
yes.
having Professor Yulong Sin from the Ohio University,
Nice.
Ohio State University. So if you have, if you see our flyers, please try to help us share our flyers to other students
Thank
here.
you so much.
Okay, thank you
Yes.
very
Bye.
much, everybody. Bye bye.
Thanks a
So
lot,
Victor,
everybody, for
yeah,
joining, and thanks a lot, Julius, for the organization. Once again, it's really, really nice of you to organize these sessions. So thanks a lot.
yeah, thank you so much, Victor. Thank you very much for your very wonderful
I'm
presentation.
very happy.
Yeah, bye-bye.
Once
Yeah,
again, if
bye-bye.
anybody has questions or whatever, my inbox is open. Don't
Okay.
hesitate.
All right. Thank you so much.
See you.
Bye-bye. See you. Bye-bye. Yeah.
Bye.
Bye-bye. Bye.
Have a good evening.